Okay, so today we will talk about waves, and waves are a phenomenon where the position versus time graph for the object or the particles will look something like this. So this is your position, this is time, and for a wave, you have something that's oscillating back and forth. Now there are two types of waves. And the difference between the two deals with the direction of the velocity of the wave with respect to the oscillation of the particles that make up the wave. So the first type is longitudinal. And these are waves where the particles oscillate in the same direction as the velocity of the wave. And an example of this would be sound waves. And the other type of wave is a transverse wave. And for transverse waves, the particles oscillate in the plane perpendicular to the direction of the velocity. And so an example of this are light waves. So for light, the electric and magnetic fields oscillate perpendicularly to each other, and then the direction that that light wave propagates is perpendicular to both the magnetic and electric fields. The other example of a transverse wave would be, for example, waves on an ocean. For that, the individual water molecules just move up and down the wave, but then the actual phenomenon of the wave propagates across the surface of the water. But the individual water molecule just moves up and down within the column of the wave. So we'll remember that we said that waves, we're going to talk about waves now because they are similar to the simple harmonic motion that we've been learning about. And one of the ways that they're similar is that the graph of position versus time looks similar. And so we saw that on the position versus time graph, this was the period t, and this was the amplitude. And so this will be true for waves or simple harmonic motion. And now another graph we could make with waves that might look the same. And the difference is what we plot on the different axes. So this could be just a regular X versus Y coordinate system. And then your wave is propagating like this in the X direction. So this is the direction of propagation.
And so if you look at this graph now, the distance from the peak to the peak is no longer a time because this is not a time axis, it's a distance axis. So now this is the wavelength, which we represent with the Greek letter lambda. And then this would still be the amplitude. And so depending on which graph you're looking at, the distance from peak to peak is either the period if the x-axis is time, or its wavelength if the x-axis is a distance. Okay. So because waves move in a direction, they're going to have some velocity associated with them. So that would just be v, which is the velocity. And so now we'll have a relationship between v, the wavelength, and the period. So wavelength is a distance, and period is a time, and velocity is change in distance over change in time. So the velocity for a wave would just be the wavelength divided by the period. Or if you remember that period is 1 over frequency, then velocity is lambda times frequency, or wavelength. Oh, and so these wavelength and frequency are kind of related to each other. And basically, if you increasing frequency means that you decrease the wavelength. Or if you decrease the frequency, then you increase the wavelength. So, and the reason for that is that the velocity, it will depend on the kind of wave, but for example, sound or light, the speed of sound and the speed of light are determined by whatever medium they're traveling through. So the speed of light in a vacuum is the 3 times 10 to the 8 meters per second. But the speed of light in air or in water is different than that. And then for sound, sound can't propagate in a vacuum like light can, but sound can propagate in air or water, or it can also propagate through solid materials, which is something that light can't always do. But so because that speed is set by whatever medium you're traveling through, you can take it as a constant as long as you stay in that medium. And so if the left-hand side is constant, then if I increase one of the terms on the right-hand side here, then I have to decrease the other one to compensate. So any questions about that? And then one more thing, but maybe I'll just draw on this same slide. So if we take a look at this red line and pretend that that's nice and smooth and not pointy like that. And so this would also apply to the period graph. But if we look at this red line that we've drawn on this graph, if I were to add the y component of these two graphs together, would it make the resulting wave bigger or smaller? What's that? So if I add the red and the black line together, will it make the resulting wave bigger or smaller? Bigger than either of them. So it'll be bigger than both of them. So if this value was like 1 and this value was 2, then when I add those together, I would get 3. And then on the opposite side, down here was -2 and here was -1, then I would get the resulting answer would be down here at -3. So like the resulting, I'll try to draw it in blue. So it looks something like that. So if I add the red wave plus the black wave, I get the blue wave. And so when your wavelengths like this match up, or we'll see in a second, if your periods match up, then you get a stronger wave than you had with either of the other two. And this is called constructive interference. And so on the graph above, let's do this would be this. So now with the graph up top, if we look at the red line and the black line, if we add them together, what's going to happen? So if the red line is down here at -1, and this is up here at +1. Yeah, so if your periods are shifted like this, which would be 90 degrees or pi/2 shift, then is this 90? Then this is what's, I guess I'll do the same thing. So black plus red will give us blue. And yeah, so these will just cancel out. So you'll just get a blue line that is flat. And so this is called destructive interference.